Hello everybody. Today I would like to present my paper on the topic optimization of application deployment delay with efficient task scheduling in cloud-based smart home platform. So this shows the outline of my presentation. It contains introduction, research motivation, key problem in smart home deployment, proposed work, motivation example, result and analysis, conclusion, followed by answer to TPC question. Coming to the introduction, smart home is a use case of the IoT system to manage and control the home environment with the integration of various technology such as sensor networks, IoT system, and the cloud computing. Smart home is an adaptive and reflexive system. Installations of the home services provide saving of time, cost, and energy. The motivation of our research is to develop an efficient technique for application deployment in smart home platform. From a service provider perspective, some of the key important features points are quick and easy deployment, continuous integrations and configurations, service orchestrations, and the customization. And from the user perspective, it mainly focuses on primary home safety, environment sustainability, and easy energy efficiency, and comfort and the convenience. In this slide, we discuss the key problem in application deployment in the smart home. Generally, application deployments are done through automations. When the application size grows up, scheduling complexity is increased exponentially due to more dependency and mutual concurrencies among the hierarchical coordinated service involved in the application. In the large-scale deployment scenario, distributed scheduling to optimize the deployment delay is a complex issue because of the involvement of the large number of the loosely coupled distributed coordinated service with insufficient global state of information with transparency in the distributed environment. And practically, it's very difficult to find optimal solutions for delay-sensitive application because of the geographically distributed resources with non-standardized API. They are communicated through a lot of the networking latencies and the different bandwidths. uh, in a smart home applications, we have a different locations where different services are deployed, and in each location different service or a task which are executed on different controller. In my representations, the yellow color mean a service which is run by the device controller, and the blue color is a service run by the cloud controller, and the green color is the one which is controlled by the network controller. So some set of the tasks are working on each different locations, and they are connected and communicated by the communication link which has of different network being wide. And depending on the application's hierarchy or coordination relationship, the the link or the coordination between the service are more in some locations, and they have to communicate and execute based on their dependency and representations to execute the complete application. So to successfully deploy the applications, all the tasks which are executing in a different location has to execute it based on their precedence and the dependency rule. But in reality, there are a lot of challenges in terms of computation, in terms of storage, in terms of the communications. But in our problem statement, we try to focusing on the application deployment time, how to optimize it when an application is deployed in the large application scenarios, like as we mentioned in the examples. In this slide, we explain our proposed architecture. First, we show the high-level architecture of our proposed architecture. The cloud middleware is a centralized platform built on platform as a service model. This platform coordinates with other controller with the support of the service-oriented architecture in a distributed and heterogeneous environment via like internet. It also provides a standardized API for its controller for device management, resource management, and the network management. The device controller provide the downstream connectivity with the home device via Ethernet, Wi-Fi, ZigBee, etc. The cloud controller control and manage the network, the resource infrastructure with self-adaptive resource management scheme. And we also have a software-defined networking-based network controller which control dynamically and flexibility the home networking services. This collaborative execution in the multi-domain and multi-technology environment improve the end-to-end coordination in our proposed architecture. In our example, we have an home application consisting of the 6 tasks. Out of the this 6 tasks, the first 1 and the 3 are executed in the device controller. The tasks 2 and 4 are executing in the cloud controller, and the tasks 5 and 6 are executed in the network controller. Based on their coordination relationship and their precedence constraints, all tasks are executed in their corresponding target controller, and after all tasks are executed successfully, then this application service is deployed to the cloud. This is an modification example which consists of the 12 tasks representing and cloud applications. So in this one, we have the task 1, task 4, task 7, and 11, which are executed into the device controller. Then we have task 3, 5, 10, and 12 into the cloud controller, and the rest, the task 2, 6, 8, and 9 are controlled in the end network controller. Depending on the executions configurations, the all tasks are having some particular parameters, like the circle on the top of the task number represent the execution time, and the dotted circle below the task number means the target controller for their execution, and the number within the joining edge represented a communication cost between the two neighboring tasks. So in order to deploy the task into the cloud, the first start node has to execute, and once it executes, it needs to find out which is the neighbor task of that one, and based on that one, he has to evaluate which task has to be executed based on their starting time and based on their memory consumptions. Then based on that, we assign the task and it will execute. If there is a resource conflict, it has to wait for the task has to be completed. So this task has to be evaluated until all the tasks are executed, and when the final sync task is executed, all tasks has to deploy to the cloud. So this slide talks about the system model for our IoT application deployment problem. And in our modeling, we assume that the task execution is a non-preemptive process. So once it is assigned to a controller, it has to execute until it is finished. And in the aim of our application deployment is to minimize the total application time. So we coin this term as a max span, which is a function of the decision variable starting time and the resource assignment variable. So to do the optimization, we have some kind of constraints. So some of the constraints what we assign is the resource allocation constraints, task priority constraints, and the resource task release constraints. So we try to optimize the total max span of the execution with these constraints. On this slide, we mostly focus about the proposed scheduling algorithms for our our task optimization problem. The first one we call is the task optimization algorithm, and second one we call the resource allocation algorithm. The task assignment algorithms mainly focus to assign the right task based on their priority, based on the decision variable SR, where which is the right task to execution after the completions of the predation, and which task has to be allocated based on that particular task. So the resource allocation task will focus mostly on assignment of the resource for that allocation task. So how much execution computation resource has to be allocated for that particular task. Then once the resources are allocated, the tasks are executed, it will try to complete the execution, then the corresponding resources released for their coming tasks. So every task is deployed as we mentioned, then the application is deployed to the cloud. Then next we talk about the performance evaluation metrics. So in our papers, we have some performance evaluation metrics. Some of the metrics what you use are the max span, which is the maximum completion time of the application task executed on distributed computing resource. Then we have a CCR, we call communication to computation ratio, which measures the capability of the algorithm in communication intensive and the computation intensive applications. And next we measure the speed up. So this matrix measures the scheduling performance based to sequential execution performance. And finally we call the schedule length ratio, which measure the scheduling performance of our algorithms. And next we explain the first result of our experiment. The aim of this result is to evaluate the algorithm performance on different task size and the service coordination level. So we take a number of the task size ranging from 15 to 30, and we have a different coordination levels. So what exactly we mean to by the coordination level is, for a particular task application, we measure the number of inflow and outflow of a task, and we try to increase this coordination for all the number of the applications, and we measure how it impact to the max span. So when we compare for the same setup of the configurations and try to measure with the other comparing algorithm like first come first serve and the random algorithm, our algorithm perform better in all the configurations in our experiment. And we also measure the performance of our algorithm baseline to their sequential execution. But when you measure it, our algorithms perform substantially outperform from the other comparing algorithms. And in the second result, we try to evaluate our algorithms more on the communication and computation intensive applications. When we measure the CR values from ranging from low value to higher value, and we try to evaluate the performance of our algorithm compared with the other standard algorithms. But when we do the experiment, we understand that the communication and computation has impact on the execution performance of the application. However, when you try to evaluate on different values, our algorithm perform better from other competitive algorithms like first come first serve and the random algorithm. At the same time, we also evaluate the performance of our algorithm with the other competitor, and our algorithm performs work well with other metrics, so that by comparing with the different matrices, we conclude that our algorithm has better result from the other competitive algorithms, and it works well in the different scenarios. So in conclusions, we like to mention that we propose a loosely coupled middleware-based platform architecture for application deployment, especially for SaaS model deployment. And we also understand that this application platform is extensible to other incarnations of the IoT systems. And we would like to extend our model for parallelism and concurrent execution in the multi-cloud platform, because we are able to perform efficiently even in the single-threaded based application. But when you provide for the support of parallelism and concurrent executions with the unlimited resource access from the cloud, our model will be performing better. At the same time, in the application deployment, as we mentioned, there are a lot of constraints of the network failure, software failure, and executions failure. That's why we need to integrate the fault tolerance for the support of the reliability. So at last, first, we try to answer the first question of the TCV question. That means, can you give insight to the audience into the web technology most suitable for the low-level optimization in SaaS? Are there any high-level framework for the purpose? So to answer this question, yes, most of the application deployment in cloud is done through the web application. But in order to do the application deployment using SaaS model, the technology has to support the server-side programming, and some of the existing techniques suitable for the low-level optimization in SaaS are model view architecture with web service support, then microservice architecture with standardized REST API calls. In that case, application can be executed using the expose endpoint. Then another approach is the service-oriented architecture in the distributed framework, so that any component or functionality can be added as a service to the architecture. And another thing is, some of the existing framework existing are the OASI framework, but it is an technology specific, so it can be still applicable too. And the second question is, how is your method applicable to home automation system relying on the edge node? Implementation of the edge computing technology will improve the speed and the network performance by reducing latency. However, we need to consider the limitation of edge technology. We know that what are the limitations, but some of the relevant limitations of what we need to consider when we want to integrate in our systems are compute and hardware constraints, accessibility and operation constraints. These are the things we need to consider before integrating the edge technologies to our applications. So with this, I finish my presentations, and thank you for your time and attentions. Thank you very much again.